All right, diving in today, folks, to something that's got that classic science fiction feel, but we're grounding it in, real physics. So the question is, could black holes actually be time machines?
I like where this is going already. Yeah.
Yeah, putting aside the Hollywood versions for a bit, we've got a whole pile of sources here to pick apart. We're talking articles from Astronomy Magazine, some deep Wikipedia dives, the whole black hole thing.
Right.
Then excerpts from like a textbook on relativity, even stuff about the ultimate fate of the universe and how like Einstein's gravity really breaks from
Oh,
Newton's.
yeah. The big picture stuff.
Exactly. And our goal today is pretty clear cut.
Yeah.
Can we figure out, based on what we know about the universe, if black holes could actually function as time machines?
Ambitious. I like it.
Yeah. And what are the real world limitations? What are the catches that, maybe people don't expect? And ultimately, what does this whole mind-bending idea tell us about, like the very fabric of space and time?
The big questions.
Exactly. And we want to make sure you're getting those aha moments along the way, giving you the knowledge, but in a way that's engaging and fun. None of that dry textbook
Yeah.
stuff.
Make it come alive.
Exactly. So what do you think? Ready to spend some time?
Let's do it. This is where the really powerful theories we've got about the cosmos, they start bumping up against some truly bizarre, weird possibilities.
Right, right.
And the wild thing is, these objects, black holes, they're born from this extreme, contortion of space-time.
Yeah.
But they might also give us a key to figuring out time itself, which is, the most slippery concept of all.
Definitely slippery. Okay, so before we get to messing with time itself, let's make sure we're all on the same page.
Yeah, good.
What is a black hole, really?
Right.
It's not just some cosmic drain, right?
Yeah, definitely not. I mean, think of it this way. It's a region of space-time, right, where gravity has gone completely haywire. It's so strong that nothing, absolutely nothing, not even light, can escape once it crosses a certain boundary.
Yeah.
That point of no return, that's what we call the event horizon. And it's not just some sci-fi plot device. This comes straight from Einstein's General Relativity, which totally changed how we understand gravity itself.
Okay, so how do these regions, these incredibly dense regions of space-time, how do they even form in the first place?
Well, the main way we know is from the death of stars, but really massive ones, like giants.
Right.
When these stars, they burn through all their nuclear fuel, they can't hold themselves up anymore against their own gravity.
Right, everything's pulling inward.
Exactly, and their cores collapse, catastrophically.
Ah.
If what's left of that core is massive enough, it just keeps shrinking and shrinking until, boom, black hole.
So that's one way. All right.
Yeah, then we've got these supermassive black holes, and we're talking millions, even billions of times the mass of our sun.
Huge.
Yeah, lurking at the centers of most galaxies, how those formed is still a bit of a puzzle. Could be from, direct collapse of a ton of gas early in the universe, or maybe they grow over time, swallowing up stars, merging with other black holes.
So either way, we're talking mind-boggling amounts of mass packed in there.
Definitely.
Now, besides just being, super dense, what else really defines a black hole? Our Wikipedia source, it breaks down some key parts.
It does. Let's hit the highlights.
Yeah.
First up, the event horizon, that one-way ticket we were just talking about.
Right, the point of no return.
Exactly. Anything crosses that. It's gone from the outside universe. Then you've got the singularity. That's the theoretical heart of the black hole, where all that mass gets squeezed into a point of theoretically infinite density.
Infinite, okay.
Yeah, and the singularity itself is a tricky one. Our current physics, it just kind of breaks down there. We're pretty sure that some future theory combining quantum mechanics and gravity, that'll give us a better picture.
Right, filling in the gaps.
Yeah, and maybe it'll even show that this point isn't truly infinite. Now, early work on this by Eddington and Lemaitre,
Right.
they actually showed that what looked like a singularity at the event horizon of a non-rotating black hole, it wasn't a real physical barrier, more like a quirk in the math, a coordinate singularity.
So it's more about how we describe it with equations, not an actual physical thing at that edge.
Exactly, and that was a huge step in getting a better grasp on black holes.
Okay, so we got the event horizon, the singularity, what else?
Right, well, a lot of times we see this swirling disk of matter called an accretion disk forming around black holes. It's stuff being pulled in, gas, dust, even shredded stars.
Wow.
And as it falls in, friction heats it up to crazy temperatures so it glows really bright.
Okay.
These systems, they can get so luminous that they become quasars, which are some of the brightest things we see in the whole universe.
Quasars, right, I've heard of those.
Then there's the photon sphere. That's where light itself can actually orbit the black hole. though those orbits aren't stable. And for black holes that spin, there's this zone called the ergosphere, just outside the event horizon, where the black hole's rotation is dragging space-time along with it,
Okay.
so strongly that nothing in there can actually stay still.
It's like being caught in a whirlpool, but with, space-time.
Yeah, pretty good analogy.
Okay, so we've got a decent picture of what we're dealing with here. Now to even start thinking about time travel,
Well,
we got to dive into Einstein's big idea, general relativity, and this whole concept of space-time.
right.
It's not just separate boxes of space and time anymore, is it?
Nope, not at all. Einstein's theory, it was a radical shift from Newton's view of gravity as a force that pulls things together. Our textbook excerpt reminds us was partly inspired by Maxwell's work on electromagnetism, the realization that the speed of light is constant for everyone.
Right, for all observers.
Exactly. So special relativity, it already had unified space and time into this four-dimensional fabric we call space-time.
Okay.
General relativity then explained how this fabric can be warped, molded by gravity.
So we've got space-time, we've got it being warped. What about these things, light cones and geodesics?
Ah, yes, those are crucial.
Can you shed some light on those for us?
Sure, so space-time, as we said, it's the arena where everything in the universe happens, all the events.
The stage for the cosmic play.
Exactly, and we often visualize it using these space-time diagrams where, one axis is usually time, the others are space.
Right, like a graph.
Yeah. Now, light cones, they're really important for any event in space-time. The light cone shows you the boundary of all the future and past events that could be connected to it by signals, things traveling at or slower than light speed.
Okay.
Imagine it like a cone extending from that event. The future light cone, that's where signals from that event can reach. And the past light cone, that's where signals could have come from to affect that event.
So it's like a map of what can possibly influence what, or be influenced by what.
Precisely. Now, geodesics, they're the straightest paths an object can take through this curved space-time, when something's moving under gravity alone, like a planet around a star.
Hmm.
It's basically following one of these geodesic paths.
Okay.
It's not being pulled in the old Newtonian way. It's just following the natural curves in space-time that the star's mass created.
So gravity is less like an invisible string and more like the curves built into a bowling alley.
That's a good way to put it.
And this warping of space-time, it doesn't just affect how things move, it also messes with how time itself flows.
You got it. And that brings us to time dilation.
Which is, let's be honest, one of the most mind-blowing things to come out of relativity, special in general.
For sure, it's this idea that time can flow differently for different observers depending on their situation.
Right, like it's relative, hence the name.
Exactly. Special relativity tells us that if you're moving really fast compared to someone else, your time will actually pass a bit slower than theirs.
That's the twin paradox thing.
Yeah, exactly. But general relativity adds another layer, gravitational time dilation.
Right, which is what we're interested in with black holes.
Right, and here, the stronger the gravity you're in, the slower time passes for you compared to someone in weaker gravity.
Our sources, the astronomy magazine articles, the relativity textbook, they all really emphasize this point.
It's key.
Okay, so let's dig into that gravitational time dilation, especially when we're talking about being near a black hole. How extreme does this time difference get?
Very extreme. Imagine something falling towards a black hole.
Okay.
From the viewpoint of someone far away, not near that intense gravity, time for the falling, if they could send signals back to the distant observer, those signals would arrive further and further apart, and the light from the object would get stretched to lower frequencies, redshifted, as it fights that strong gravity.
Wow.
The Schwarzschild metric, which describes space-time around a non-rotating black hole, it shows exactly how the rate of time depends on your distance from the black hole center.
Okay, so let's say someone was really, really daring, or maybe just clueless, and they decided to orbit super close to a black hole,
Oh.
right? Just skimming the edge of the event horizon. Then somehow they managed to get away and return to that distant observer. What would have happened to them?
Well, in theory, because they were in such strong gravity, way less time would have passed for them than for the distant observer.
So they'd be younger.
Effectively, yeah, they'd have traveled into the future relative to the people they left behind, the Astronomy Magazine article. It probably mentions this as a type of one-way time travel.
Right, forward only.
Yeah. But we gotta be real, the conditions near a black hole, especially a stellar mass one, they'd be incredibly hostile.
Yeah, I'd imagine.
You'd be talking immense tidal forces. They could rip apart anything way before it even got near the event horizon.
Okay, so forward time travel, it's possible, at least in theory, thanks
No.
to black holes, but it comes with some serious risks.
Definitely.
Now, what about the really mind-bending stuff, the idea that people love to talk about, going back in time?
Ah, the big one.
I know rotating black holes often come up in this conversation.
They do. That's where we get into much more speculative territory, the Kerr metric, another solution to Einstein's equations that describes rotating black holes, no charge.
Okay.
And when we push these mathematical solutions, both for rotating Kerr and charged Reisner-Nordstrom black holes, to their limits, they kind of hint at the possibility of wormholes.
Wormholes?
Yeah, tunnels that could connect different spots in space-time, maybe even vastly distant regions or even different universes. The Wikipedia article probably goes into this.
So wormholes through black holes, that sounds like pure sci-fi.
It does, and you're right to be skeptical. The math might allow for it, but these things are thought to be super unstable.
Okay.
Most physicists agree that any little disturbance, even a single particle going into this theoretical wormhole, could make it collapse instantly.
So no traveling through.
Not likely. And then there's the Kerr singularity. At the center of a rotating black hole, it theoretically allows for these things called closed time-like curves.
What are those?
Basically, they're paths in space-time that loop back on themselves,
Okay.
meaning if you followed one, you could, in principle, go back to a point in your own past.
So you'd meet your past self.
That's the idea, and that brings up all sorts of paradoxes, the classic one being the grandfather paradox.
Right. If you go back and stop your grandfather from meeting your grandmother, you'd never be born. That sounds like it's meant to stop those time travel paradoxes.
Yeah, the cosmic censorship hypothesis, it's a fascinating idea. It tries to resolve these problematic scenarios. Basically, it says that singularities, those points of infinite density where physics breaks down, they're always hidden behind event horizons.
Okay.
So you can't have what are called naked singularities, which would be visible and might allow for things like traveling on those closed time-like curves, violating causality.
Right. So no messing with cause and effect.
Exactly. Now, cosmic censorship hasn't been proven mathematically, but a lot of physicists accept it. There's support from theoretical arguments and simulations.
That's a pretty strong idea.
Yeah, it suggests that nature has a way of protecting us from those paradox situations.
So the event horizon, it's not just an impenetrable barrier in space. It's also a barrier against going back in time.
That's a really good way to think about it. Once you cross the event horizon, all paths inside lead to the singularity, and you'll get there in a finite amount of your own time, your proper time.
Yeah.
You can't turn around and get back out.
No escape.
Nope. So, no way to travel back to your past outside the black hole either. From the distant observer's view, remember, someone falling in takes forever to reach the horizon due to the extreme time dilation and redshift.
Right. They never actually seem to cross.
But for the person falling in, it's a one-way trip to the future relative to the outside universe.
Okay.
And this asymmetry is crucial. You can enter the black hole, moving towards its future, but you can't come back out to its past.
All right, so that pretty much rules out going back in time through black holes. But then there's Hawking radiation, which tells us black holes aren't entirely black, right?
Ah, yes, Hawking radiation, a real game changer.
Does that change anything about what we've been talking about, maybe in the very distant future?
It does raise some big questions that we don't have answers to yet. Hawking radiation shows that black holes aren't just sitting there. They actually emit a tiny amount of thermal radiation, and that's due to quantum mechanics happening near the event horizon. This radiation carries away energy, so black holes actually lose mass very, very slowly over incredibly long times.
They evaporate.
Exactly. And the more massive the black hole, the longer it takes to evaporate.
Right.
The lifetime is proportional to the cube of its mass, so eventually, theoretically, a black hole could completely disappear.
And this evaporation, does it affect the time machine stuff we've been talking about?
It does bring up some profound questions, like what happens to all the information about the stuff that collapsed to form the black hole in the first place?
Right, as it evaporates away.
Yeah, does that information just vanish? That would violate a key principle in quantum mechanics, that information is always conserved.
Right.
Some theories, like the holographic principle, which the Wikipedia article might mention, suggest that all the information could be encoded on the surface of the event horizon itself.
Interesting.
But in terms of time travel, if black holes evaporate, then any time machine properties they might have would also be temporary, ultimately governed by the laws of quantum gravity, a theory we don't have yet.
So even if a rotating black hole could be a pass to the past, it might not be around long enough to make that journey.
That's one way to look at it.
It seems like for every potential way to go back in time, physics shuts it down.
That's pretty much where we're at with our understanding. General relativity might open up some crazy possibilities with black holes and time, like that serious time dilation that lets you maybe travel to the future.
Right, one way.
But going back in time via these things, it's full of theoretical roadblocks, logical paradoxes, probably fundamental instability.
Right, it all breaks down.
And the cosmic censorship hypothesis, which is pretty widely accepted, suggests the universe might have a built-in way to stop those scenarios that would let you observe going back in time.
Okay, so for our listeners trying to wrap their heads around all this, it
Yep.
sounds like black holes are more like one-way tickets to the future, and even that's a risky trip.
That's a good summary.
The past, at least according to our current physics, is off limits, even with these fascinating objects.
Yeah, that's accurate. And what's really amazing is how studying these extreme environments pushes our understanding of space, time, and gravity to its limits.
It's like the universe is testing us.
Kind of. And the fact that we can even think about these huge questions using these complex mathematical frameworks like general relativity, it shows the power of human curiosity and the scientific method.
What does that tell us about the very nature of reality where quantum mechanics meets gravity?
Big mysteries.
Those are the kinds of questions that keep physicists up at night, and we hope they keep you thinking too, long after this deep dive is over.
Food for thought.
Exactly. Thanks for joining us as we explored these mind-bending ideas really at the edge of what we know.
My pleasure. Always a stimulating trip into the weirdest parts of space time.